Okay, it is coming out exactly parallel to the original path in which light was supposed to travel. Now this perpendicular distance between these two rays which are parallel to each other, okay, one was the original direction and now one is the current direction in which the light is traveling. This particular perpendicular distance is known as the lateral shift. Okay, this perpendicular distance between these two rays of light is known as lateral shift, and this lateral shift is determined by the formula t equals to t sin bracket में I minus r1 upon में cos r1. Okay, I have told you this is the formula for general lateral shift amount. If you want to find out the or calculate the maximum lateral shift, in that particular situation your I equals to 90 degree and r1 becomes 0. Then d equals to becomes t. That is your maximum lateral shift. Okay. Next concept which I have told you about was real depth and apparent depth. Okay. And what was the meaning of real and apparent depth? Let's see. I told you that in this particular concept, what really matters is the placement of the object. If your object is placed in denser medium and you are observing from rarer medium, suppose there is a block of object of mass, it is present inside the water. Okay, water is here and it is present here, and you are observing from above the water, that means air. Okay, in this particular situation, my real depth is going to be different, apparent depth is going to be different. What really happens? Light is going to travel from in this particular situation from denser to rarer medium. Okay, in another condition, what will happen? I can be present in the denser medium and I am observing the object, okay, which is placed in the rarer medium. In that particular situation, my apparent depth and real depth situation is going to be different. In the first case, my real depth will always be greater than the apparent depth. And in second scenario, when the object is placed in the rarer medium and I'm observing from the denser medium, your apparent depth is always going to be greater than the real. Okay, and which formula governs or tells about this particular situation? The formula is 1 into, I have derived it for you, 1 into equals to real depth upon apparent depth. Okay, in the situation of when the light is traveling or in this first particular situation. If second thing happens, your formula becomes 1 upon 2 n1. Okay, so in this particular situation, I already also told you there is a difference between these two particular heights, real depth and apparent depth. And whenever you try to find the difference between the real depth and apparent depth, that is known as your normal shift. Okay, so normal shift is basically the difference. Okay, it is denoted by x. It is denoted by x, and it is the difference between the real depth and apparent depth. In both the cases, now you can understand it is going to be different. Normal shift here will be different, and in this particular situation, it is going to be different. Okay, and the formula which finally comes out is, okay, it depends on the thickness of the object as well. So the formula will come out as x equals to t bracket में 1 minus 1 upon n. Okay, so till this point we have covered in the previous section. Okay, I have given you all the idea behind it. Okay, now we are going to move forward. Okay, now the next topic is phenomena related to refraction of light. Okay, phenomena related to refraction of light. Okay, now what are the phenomena which I can find inside the nature that can be explained by the use of the refraction of light? Okay, and to understand this particular thing, okay, one of the natural phenomenon which is related to refraction of light is your twinkling of stars. Okay, twinkling of stars. Now what we have to do, we have to understand yes, refraction of light is happening there, but what exactly is happening? What particular mechanism is making stars blink, okay, or changing its position? Okay, it feels like that one moment it is blinking, and the next particular moment it is coming back again. Okay, so what really is happening in this particular situation is the concept of your apparent position, okay, or real position, because of the fact that he light, when it is coming from the stars, it is going to enter our atmosphere, and in the upper layers there is rarer medium, okay, and on the lower levels it is denser medium where we are present, okay. And when the light is going to come out, suppose it is existing here, it is here, and when it is going to enter like this, okay, what will happen? Light will bend a little bit close to normal like this, okay. So for us, a little bit like this, okay, the actual star might be here, okay, but due to the process of refraction, what happened? Its position changed. Now it will feel like that it is here, okay. This apparent position change is due to the refraction of light and our concept of but real depth and apparent depth, I cannot exactly apply it here because of the fact that the distance is too high, okay. So we are just going to apply the refraction process here, okay. Now these particular mediums, okay, the atmosphere is a continuous movement of air, so this cannot be said like it is going to happen once, only one time. The process of refraction is happening on the continuous basis. And this continuous change in the apparent position of a star leads to the twinkling of stars. Okay. So now this is the explanation behind the twinkling of stars. Now, second phenomenon which you must have witnessed, okay, regarding refraction of light, it is known as bending of an immersed object in a liquid. Okay, you must have done this particular experiment at your home. Okay, what really happens? You take a glass of water. Okay, this is glass. Inside there is water, and what do? You drop your pencil into it. Okay, but somehow this pencil looks a little bit bent. Okay, it is not exactly straight, but in reality it is. But the moment you insert it inside the glass, now it feels like a bend. Okay, there is a bend in the pencil here. So what exactly is doing that? What is making the pencil to bend? Okay, and this we have to understand that the refraction process is behind it again. Okay, in this particular situation, what is going to happen? Yeah, the object, okay, it is inserted in the inside the water, okay, and when we are going to look at it, okay, this deep point here, this particular point, okay, it, the light ray will come from here, okay, and they will travel to our eyes like this. So light is going to travel from denser to rarer medium, and because of that, again an illusion is going to be created, okay. The actual position of this particular dip is going to be here, but in our mind it is going to be here. So that is the illusion, and that because of that, it is the illusion has been created, the light, that particular object has bent, or the pencil has bended, okay. So this is the explanation behind it. The next particular phenomenon which is attached or related to the refraction of light, okay, which everybody must have seen, that the size of the sun, okay, whenever there is a morning, okay, in the morning or in the evening, okay, at both the times what happens, the position is exactly the same for the sun, but the horizon, okay, if earth is placed like this and sun is like this, okay, like this, what exactly is happening? Earth is rotating from west to east, west to east. Suppose when the morning happened, when we were here, and throughout the whole day we came up to this point. Okay, when the morning happened, we were, this location was about to come in front of the sun. Okay, so this is known as horizon point. Now, when the light is going to fall on this particular point, okay, what will happen? Light is going to enter inside the atmosphere, and there is a bit of refraction. Okay, so the upper point of the sun and the lower point of the sun both will give out the different light rays, and both will have different positions because of the refraction of light. And because of that, there is a slight increase in the size of the sun. Okay, that is why in the morning and in the evening, the sun appears to be oval shaped. Okay, oval shaped in the morning and evening. So, what simply happened? The rays of light from the upper and lower edge of the sun, they are going to bend unequally. Okay, and this unequal bending of the light rays from this particular point and this particular point is going to lead, okay, uh, to the increase in the vertical diameter of the sun. Okay, now what is the solution behind it? What is the real size which you can see of the sun? That happens at the noon. Okay, at the noon, sun is directly above you. Okay, and the rays of light is going to enter the atmosphere directly at the normal. Okay, and whenever in refraction light is going to travel at the normal, there is not going to be any process of refraction. In that particular situation, you are going to see the sun's original or real size. Okay, and also the correct amount of light which is uh, it is sending to the earth. Okay, in reality the sun is white. Okay, in the morning and in the evening, it appears to be a little bit yellow and red, which is not the correct or true character of the sun's light. Okay, the light which is coming from the, yes,
Yes.
do you have any doubt? Okay, if you have any doubt you can ask anytime. Okay, now in this particular situation, when at the noon the light is going to fall directly at the normal, there is not going to be any particular refraction process, because when the light travels at the normal, there is no angle of incidence and there is not going to be any angle of refraction. Both are 0 degrees. Okay, and this particular concept I told you that this is a bit related to the thermal radiation giving out by the objects. Suppose you heat iron. Okay, when you heat iron at particular point, it is going to emit out the radiation. It becomes so hot that it is going to emit out the colors as well. There is thermal radiation attached to it, plus also the amount of radiation which is going to come out from the visible light portion. That is why you see colors. So at a particular temperature, suppose 300 degrees Celsius, it might appear to be red in color. Little white later, if you provide it much temperature again and again, it will become a little yellow. Okay, and at 6000 degrees Celsius, it becomes white. So sun gives us around white light. So the temperature of photosphere on the outer surface of the sun, it the temperature is 6000 degrees Celsius. Okay, so this is it. Now, the next object which is related to the refraction of light, we are going to cover it in a little bit deep. See, the next concept is total internal reflection. Total internal reflection. See, we were studying the refraction of light. So, how exactly now the reflection process is coming here? Okay, this particular phenomenon is a bit interesting. Okay, first, what you have to understand, there are conditions attached to the total internal reflection. Okay, this particular phenomenon only happens in certain conditions. What are those conditions? First condition is the light should always travel from denser to rarer medium. Denser to rarer medium. Why? Let's see. Take. Suppose this is your air and this is your water, and there is object which is placed here. This is emitting out the light. Okay, so light will come out like this. Okay, this is my normal. Okay, now when the light will exit out of the water, this is my interface. This is the barrier between the air and water. Okay, when the light is going to exit out of the water and enter inside the air, it will bend away from the norm. Okay, that is what refraction process, okay, has told us. From rarer to denser, it bends towards the normal. From denser to rarer, it bends away from the normal. So in which direction it is going to bend? Away from the normal. So the meaning is, if I keep on increasing my angle of incidence, my angle of refraction is going to be maximum. And there will come a particular point my angle of incidence is going to reach criticality. Okay, what it is going to reach? Critical point when the angle of incidence has going to be increased to a particular point that your angle of refraction angle has become 90 degree. That means the light is going to travel now on the interface. Okay, my angle of incidence has become a critical angle at which point R is going to become 90 degree. And this particular point is the tipping point. Okay, tipping point means after that, furthermore, if I keep on increasing the angle of incidence, what will happen? Now the refraction is going to stop completely. Okay, the refraction process is going to stop completely and light is going to come back to the same medium. Okay, so in this particular situation, what will happen? If you increase the angle of incidence further, refraction stops and reflection starts. Now the light is going to coming back to the same medium. Okay, all the time. So this process is known as total internal reflection. Okay, the condition is here. It should travel always from denser to rarer medium. Now, what happens when the light is going to travel from rarer medium to denser medium? See, okay, this is my angle of incidence. Okay, one second. Okay, angle of incidence. Now, when it is going to travel from rarer to denser medium, what happens? The light bends towards the normal. That means if you keep on increasing your eye angle of incidence in rarer to denser, okay, phenomenon, then what will happen? You keep on increasing your angle of incidence, light is going to travel, okay, exactly at one point at normal. That means my R is going to become 0 degree, which is opposite. Okay, exactly opposite. And that is why what will happen? Light will never come back to the same medium. Because after that, you keep on further increasing, the light will always travel to the normal. And this particular barrier stops TIR, total internal reflection, to happen in rarer to denser phenomenon. Okay, so this particular TIR process is restricted to this particular concept. Okay, it will always happen in a process where the light is traveling from denser to rarer. Now, the second particular condition about this is that the angle of incidence must be greater than the critical angle given for the pair of mediums. The meaning is, see, which I just have told you. In this particular situation, the pair of medium I have taken is air and water. But in certain other conditions, this pair of mediums can be changed. But it will always, one is going to be rarer, another is going to denser, and light is always going to travel from denser to rarer medium. Only in that particular situation, TIR will happen. So first condition has met. Second, your angle of incidence must be greater than critical angle. So that means for a pair of medium, there must always be a critical angle, okay, which the light has to achieve in order to attain the total internal reflection. Okay, this particular concept, okay, now has given you a lot of advances in the technology as well. Okay, we are going to see how. Now, mathematically, first we have to see how exactly it explains. See, in this particular situation, what is going to happen? Here, the light is traveling from second medium. This is my second medium. This is my first medium. It is traveling from second medium to first medium. So, how I am going to write this particular process of refraction? It is 2n1. Okay, if it is 2n1, what will happen here? Okay, your angle of incidence is inside, so it will be written as sine I upon sine R. Okay, this is how your process of refraction is going to be written down in terms of Snell's law or mathematically. Now, when the TIR happens, okay, there is a tipping point, and that tipping point is that your when your angle of incidence is equal to C, R becomes 90 degrees. This is my tipping point. Okay, so if I introduce this particular condition in my calculation, what will happen? I will enter these particular information inside this Snell's law equation. See what will happen. It will be written as now 2n1 sine I will become sine C and sine R will become sine 90 degree. Now sine 90 degree has the value of 1. That means this will become, okay, 2n1 equals to sine C. Okay, so this is our result. This is our result, or it can be further written down as 1 upon, okay, 1 and 2 equals to sine C. Okay, as simple as it can get, or you can write it down as 1 and 2 equals to 1 upon sine C. Okay, you can write it in these particular modifications. Now this particular equations tells us that this is my relative refractive index, and this is my critical angle. The meaning is there is a particular relationship between relative refractive index and critical angle. If your relative refractive index is higher, that means your critical angle has to be low. Okay, it is an inverse relationship. Okay, let's see how it is given. See, my formula says 1 and 2 equals to 1 upon sine C. Okay, the explanation here is that your relative refractive index is inversely proportional to the critical angle. That means if your critical angle is low, so the lowest critical angle is for the diamond. Okay, if your critical angle is low, that means it is going to have the highest refractive index. Let's see what the diamond has. The diamond has critical angle of 24.41 degree. Okay, and exactly its relative refractive index comes out as 2.42. So now if I increase my critical angle, suppose around 45-46 degrees, now there is water which has a critical angle of 48.75 degree, and its re- relative refractive index comes out as 1.33. Now these calculations are justified this by this particular equation. Okay, the meaning is this is in totally correct form. Okay, there is no doubt that this is not correct. Okay, now during total internal reflection of light, the whole incident light energy, okay, is reflected back to the parent optical denser medium. Whenever the TIR is going to happen, the whole light energy is going to be reflected back. Some might be absorbed a little bit here and there, but in totality, it comes out as the original energy. Okay. Now, TIR process, okay, this particular TIR process is responsible for a lot of uh, phenomena happening inside the nature. Okay. But before that, I'm going to tell you about the critical angle, okay, of a medium depends on the wavelength of a light in a certain manner. How exactly? Let's see. Your critical angle of a medium, okay, its dependence upon the wavelength of light. Okay. Now, your relative refractive index or your absolute refractive index, they has a value of, like, in mathematical term, it comes out as n is like inversely proportional to 1 upon lambda square. And because of that, your sine C is also comes out related to as directly proportional to lambda square. Okay. So this particular relation, okay, gives us a relationship of critical angle to the wavelength of light. Okay. Now, the greater the wavelength, suppose The more the wavelength is, the greater the wavelength, greater will be the critical angle also. Okay. If the wavelength is more, that means the critical angle is also going to be more. Okay. So critical angle of a medium will be maximum for which color? Now you can easily say, if I say there is like Vibgyor colors, okay, out of these colors, now you know that red has the maximum wavelength. So for maximum wavelength, which is the red, okay, red has the maximum wavelength. My critical angle is also going to be greater for this, and it is going to be minimum for violet color. Okay, so this particular concept explains this phenomenon. Second, I have also told you कि whenever you were taking the ratio of like absolute refractive index in terms of wavelength, it was coming out as lambda upon lambda m. Okay, this also explains the same thing. Okay, when you put this value, then for sin C, this value is going to be lambda m upon lambda. Okay, now critical angle depends upon the nature of the pair of media as well. Okay, greater the refractive index, lesser will be the critical angle. Now, if there are images which are formed due to the total internal reflection, okay, they could be brighter, okay, because the total light is reflected back in the same medium. Because of that, there is no loss of intensity of light most of the time, a little bit here and there, but maximum greater than 99% is there. Okay, not absolute. And because of that, what happens, the energy which was supposed to be distributed in two mediums has come back to the same medium, only first uh, medium, okay, from which it has traveled. The intensity of light is going to be remaining same, and the image which will form is going to be equally brighter in nature. Okay, so this particular concept explains. Now, in questions or you will see a lot of times simply they have asked you to calculate either the refractive index or the critical angle value. Okay, so this is how they have asked the questions, or directly they can ask a lot of conceptual data. They can give you like statements related to TIR. They will give you three statements, and they will give you options whether 1 and 2 is correct, 2 and 3 is correct. Like these questions can be formed. Okay, so you must practice a bit of PYQs to understand in which particular nature the questions is going, or they are asking the questions. Okay, now there are applications attached to the process of total internal reflection. Okay, so our next topic is applications of total internal reflection. Total internal reflection. 1 second. Okay, so our topic here is application of total internal reflection. See, there is a lot of applications you will find, okay, for total internal reflection, but it has been like accurately given, or inside the lab, the working of TIR has been checked by a particular device which is known as poroprism. Poroprism. Now, how exactly this poroprism is? Inside the poroprism, these particular opposite sides, they are at a 90-degree angle. They are balanced at a 90-degree angle, and the base is at around 45-degree each. Okay, this particular combination, okay, gives us an advantage that when light is going to enter in a certain matter like this, it is going to be exactly reflected back in a certain manner. Okay, like it is going to make at both the times 45-45 degree. So there is a particular phenomenon. Okay, the light is going to bend exactly according to the calculations. Okay, so this particular poroprism, this is a right angled isosceles prism. Right angled isosceles prism. Okay, this is known as poroprism, and this can be used. What is the use of the poroprism? This can be used in a periscope. okay, or a binocular, okay, in the formation of either periscope or binocular. Now, total internal reflection, I told you, it can be easily calculated. Now, the right angle prism here, it most of the time is used to invert the image of the object. Okay, whenever you want to invert the image of a particular object, you will use these particular phoroprisms. Okay, now we have seen कि देखो in phoroprism whole light is going to be reflected back. Okay, and I told you in TIR there is hardly any loss of intensity. Okay, so the image is always going to be bright. Okay, though it is going to be inverted image, the image is going to be bright. But if you're going to use like mirrors, okay, in mirrors most of the time intensity of the beam is reflected, but intensity is a little bit low because sometimes the polished mirror absorbs a little bit of light energy. Okay, so the image formations created by mirror and due to a poroprism, both is going to see a difference between the intensity of the image or the brightness of the image. Okay, or this particular concept can be used in making a particular PYQs. Okay, the next concept, which is related to the total internal reflection, okay, it is sparkling, sparkling or brilliance of a diamond, brilliance of a diamond. Now everybody has seen diamonds, okay, at least in the movies or on online. Okay, now what is the property related to diamonds? That they sparkle. Okay, they sparkle meaning चमकते हैं, उनमें चमक आती रहती है और वो चमक आने के लिए दैट मीन्स लाइट इज गोइंग टू बी रिफ्लेक्टेड बैक. टीआईआर का प्रोसेस यहाँ पे हो रहा है. ठीक है, अब मैंने आपको बताया था इन द प्रीवियस क्लासेस और थोड़ी देर पहले भी कि व्हाट एग्जैक्टली हैपेंस हियर कि व्हेन द टीआईआर इज गोइंग टू हैपन योर फॉर्मूला डिक्टेट्स दैट 1 and 2 should be like this sin c. If critical angle is low, your refractive index is going to be high, and that was the case related to diamond. Okay, diamond has a very low critical angle which is 24 degree. So the meaning is कि light can come from any direction. It is always going to be greater than 24 degree in most of the cases, and that is why in most majority of the cases light is going to be reflected back. PIR is going to happen pretty much from all the directions. Okay. Secondly, when the jeweler takes the diamond, they shape the diamond and outer shape is giving a clear cut geometrical shape so that this particular critical angle can be lowered further down. Okay. And because of that, the sparkling amount increases. Okay. So this is the particular reason behind the sparkling or brilliance of a diamond. Okay. Now, because in most of the cases where this particular diamond from every direction when you're going to look at it, it is going to reflect back the light, and because of that the sparkling is happening. Now the same thing accidentally when you uh, randomly take the soap water, okay, and you blow out the bubbles and those bubbles are shiny in nature. Okay, somehow the critical angle for the water air interface, I told you, it is around like 48 degree. Okay, when light propagates from water, okay, and which is like denser medium to the on the surface of air bubble. ठीक है, अब the total TIR is going to take place. अब that is why in most of the cases when the bubble happens from some angles it is going to shine a little bit. Okay, that perfectly is the explanation for this particular topic. Okay, the next particular application or the phenomenon related to the total internal reflection is of the mirage. Okay, so first let's explain what mirage is. Okay, the concept of mirage is directly associated with TIR. Now, what is mirage? You must have seen कि गर्मियों में आपने अगर आप कभी भी रोड पे ट्रेवल कर रहे हैं एट फर्दर डिस्टेंसेस, बहुत ही दूर पे डिस्टेंस पे आपने देखा होगा कहीं आपको लग रहा होगा अरे यहाँ पे तो रोड पे पानी है आगे जाके. ठीक है, दैट पर्टिकुलर इल्यूजन यू थिंक दैट वाटर इज देयर, बट व्हेन यू रीच दैट पर्टिकुलर पॉइंट द वाटर इज नॉट गोइंग टू बी देयर. Okay, so basically this is an illusion. Now what, how exactly it is happening? Okay, what is the reason behind it? Why only the water is shown? In majority of the cases, only you see water at a larger distances. Okay, in few cases, there might be cases where you see the uh, inverted images of the object. Like when you're traveling in a particular desert, suppose you're in a desert region, what is going to happen? Suppose this is my surface, ground surface. Okay. Now, if you're traveling, suppose there is a camel here, okay, and you're sitting on the top of it, okay, like this, and at a particular distance, there is a tree, okay, at a very further distance. What is going to happen? The air which is in the contact of the ground surface, when the heat is very much high, when the at the noon time, the temperatures is going to be very high. Because of that, there is a lot of heating of the ground, and when the ground heats up, the air in the contact also heats up, and when the air heats up, it rises above. Okay, hot air, if you uh, give the energy to the air, okay, it will rise above. Hot air rises above. That is why your hot balloons have created. Okay, so what happens here? The heated air is going to rise above. That means it is going to create the rarer medium very near to the ground, and a little bit up on the height side, there is going to be denser medium. So this is a perfect situation now. Suppose the light is going to travel. Okay, the light comes like this. From this particular point, the light is going to fall like this. And if it crosses the critical angle, light is going to travel and reach the eyes of the observer. Okay, now the TIR has happened. Actual position of the object is this, but because TIR has happened, you will see that this particular light is coming from this point. So this will create the inverted image, and also the sky is present above us. Okay, in most of the time at further distances, this is the image of the sky which results in us seeing the water on the surface. Okay, so this is the inverted image of the sky which results in us seeing the water on the surface. Okay, so that is particularly the explanation for your illusion of mirage. Okay, and it is exactly the concept of your TIR happening at the random places because of temperature and thermal differentiation. Okay, on the surface of the earth, there is a huge variation of temperature. On the equatorial region, you will see it is very much high. On the polar regions, there is no particular. Okay, it is very cold there. Okay, so thermal variation from different places on the earth is very high, and because of this, different type of phenomenon is attached to different particular places on the earth. Okay, now mirages, mostly it is related to the hot places. Okay, so you can travel to like Thar Desert, Sahara Desert, or any place on the equatorial region. Okay, in those particular places, you can easily see the mirage happen. In India, it is very common. Okay, whenever on the like summer days, you go out, and at a further distance, you can easily see the mirage happening. Okay, now mirage is a very good concept, and a lot of questions has been asked from this particular concept. Okay, now if mirage is happening due to the high temperature, okay, this particular mirage in hot places, it is known as inferior image. The image which is going to form like this, it is known as inferior image. Okay, but cold places also kind of create a illusion of their own. Okay, there also TIR happens in some conditions, and when the image forms in those particular situations because of cold regions, that is known as looming. Okay, so in hot regions, your formation of mirage image is known as inferior image, and mirage happening inside the cold regions, it is known as looming. Okay, the next concept now we have, or the next phenomenon which is related to the total internal reflection, is optical fiber. Okay, I have already told you that the application of total internal reflection has made a huge advancement in the technology, and that advancement is your optical fiber. Okay, optical fiber. So what exactly is optical fiber? Okay, so see, basically what happens, In optical fibers, what we are going to do is we are going to create a wire. Okay, in this particular wire, what are we going to do? We are going to take a inner material which is going to be denser in nature, like this. Okay, and we are going to put a coating outside, like we used to coat plastic. We are going to put a coating outside this material which is going to be of rarer in nature. That means in comparison, the optical density of this particular inside material, it is going to be denser. Outer material is going to be rarer. And what happens? Now I'm going to take a source of light and I'm going to uh, directly place it in such a fashion that the light is going to fall inside the wire. And this now will give the process of TIR to happen. Okay, light will enter and the TIR will start to happen because the conditions of TIR has been successfully attained, because the light is going to travel from denser to rarer medium. And in this particular situation, what happens? Because the light is involved, that means the speed is going to be of speed of light, that is c. Okay, earlier whenever you want to transmit any particular data, you use the transmission rate of electricity. Okay, and in those situations the transmission of data is a little bit slower, but here you are using the speed of light. Okay, light is going to carry all the information for you. That is why the speed of transmission of data, it becomes very much high. Okay, and this particular uh, concept of total internal reflection applied into these particular uh, cables, which are known as optical fibers, has given us an advancement. Okay, so optical fiber, what exactly is it? These are basically extremely thin, okay, fine quality glass or quartz material, okay, wires or strands where the refractive index of both the mediums is a little bit different. Inside material is a denser material. Higher the refractive index is going to be different. Here the refractive index is going to be low. Okay. So this particular differentiation creates a optical fiber. Okay. Now how exactly do we use it? Use किस तरीके से होगा इसका? देखो बच्चे, first what we do कि we take all the data, okay, and we convert that data, okay, in light energy. Give me 1 second. Okay, so to change 1 second. Okay, so what happens? How exactly we use it? See, to convert, because all the data is going to be like in electric form, okay, digital form, you first take a machine known as transducer. Give me 1 second. Oh, see, what happens here? We we have to first, okay, take all the necessary amount of like information and use the machine known as transducer. Okay, what it does? Okay, this particular transducer, it converts electrical signals into light signals. Okay, or light energy. Electric energy is now converted into light energy, and then that particular light energy is directed towards the optical fibers. Okay, and then it travels at the speed of light, it reaches the destination, and again we are going to use what transducers to convert it back from light energy to again electric energy. Okay, and then again it is now forwarded. Now this particular rate of transmission in the wires, it has been increased to a significant amount because of the concept of this optical fiber. Okay, so in telecommunications, if you are like transmitting audio, video signals, okay, these are going to be transmitted at the speed of light. Okay, so basically single fiber. Okay, it has much capacity than the electric wires. Electric wires have a very low capacity of sending signals. In an optical wire, you can send the signals in multiple folds. If like electrical signal is capable of like 100 signals, this particular optical fiber can transmit, okay, around 3000 signals, more than 3000 signals at one particular time. Okay, that cannot be attained inside the electrical wires. Okay, and that is why the transmission rate and the amount of data which can be transmitted through the optical fibers is of much greater capacity. Okay, now you must have seen optical fibers in toys as well. Like whenever you must have visited any kind of mela in your region, you have seen there are objects like this and there are wires coming out, and the light is in the little strands. Okay, and this is how the whole system is there. These are a bit of explanation of optical fibers. Okay, so this is the explanation for our optical fibers. And with this particular thing, we have uh, covered the entire topic of total internal reflection. Okay. In exams, the question can be asked, okay, either for you to derive the equation, okay, or a multiple questions can be asked for you to write down a little bit amount of information on the application attached to the total internal reflection. Now we have explained pretty much everything. Now, besides these particular explanations or applications, there are some more phenomena which are associated with TIR. And those phenomena are known as rainbows. Okay, which we are going to cover a bit later. Okay, these rainbows are also based on the process of TIR. Okay, so what happens here also? The same process is going to happen. Okay, the bubbles of like water, when the water falls from the uh, clouds to the surface, those water bubbles, okay, the light enters inside them. Okay, when the light is going to enter inside the water, okay, droplet, what is going to happen? At some points, the light is going to enter, the process of refraction will take place, and when it is going to be greater than the critical angle for the water, which is 48 degree. Okay, if the incident angle is greater than 48 degree, the TIR is going to happen. The light is not going to further refracted again. It is going to come back, and then again the process of refraction takes place. So two times refraction and one time TIR happening here, which gives rise to rainbows. Okay, and this is the primary rainbow we are talking about. If process of refraction is happening multiple times, that means you will get secondary or tertiary rainbows as well. Okay, so total internal reflection is also there to explain the concept of rainbows for us. Okay, now moving ahead, we are going to move on to the next topic. If you have any doubt related to any explanation, you can ask me. Okay, the next thing. Now we have seen the process of refraction. Now we have to ask ourselves, what is exactly happening? Okay, light is going from one medium to another medium. Okay, so what exactly I can change here? Okay, the normal is like this. So similarly, what we have done in the reflection of light, what we have done, we when the reflection was taking place, there was one reflecting surface, and light used to interact with the object and bounces back to the same medium. So what we did, we changed the shape of the reflecting surface from a plane object to a curved surface. Similarly, in this particular concept, we can also do the same thing. We can take some amount of okay material, suppose a glass slab, and if I cut it in such a fashion, like I cut the outer part, I cut this outer part in this fashion, what it is going to do? Okay, this particular shape or craft we have provided it. Okay, this will give us a boost because now the normal is going to change. Earlier, it was directly at 90 degree. Now my normal is going to pass from the center of curvature like this. Okay, because only in your curved surfaces, your normal always passes from the center of curvature. And this particular concept, this normal changing in a particular fashion is going to give rise to a very different phenomenon, which will give rise to the formation of lenses. Formation of lenses. That means this has given us a concept where we can see the object in much details. Now we have found the secret of magnification. Now we have learned how to make microscopes and telescopes. So this was a huge advancement in learning how the optics was happening or how the light was behaving. Okay, different account. or around the different objects. Okay. Now, this was a great learning in terms of optics. Okay. Light's behavior or how exactly we can use this for our advancement. Okay. So this has a lot of good concept attached to it. Now, for us to understand this particular concept, this is known as this particular process is going to be known as spherical refracting surfaces, creation of spherical refracting surfaces. So the topic is spherical refracting surfaces. See, our topic is spherical refracting surfaces. See, now I have told you the outer surface of a particular, okay, you can take any particular glass, okay, or it is mostly done inside the glass material. So that is why I'm taking glass. Okay, if there is a possibility of taking any another medium that can also be done. Okay, so in this particular situation, what I'm going to do, I can either cut the outer part in a formation which will give you a concave shape when the light is going to fall. It will be falling on a concave, okay, concave refracting surface, or either I can give it a shape of like this. That outer shape is bulging like this, and this will be known as convex refracting surface. Okay, so in a concave refracting surface, what I did, okay, I made a shallow sphere. Okay, in this particular uh, convex shape, I made an outer bulge. Okay, now there are some concepts when we are going to understand this particular concept similar to mirrors. This also has have the same features. Okay, so what are these features? See, first thing, if this is my refracting surface, okay, there is going to be a principal axis just like mirrors. So this line shows us the principal axis. Okay. Second thing, because of the curved nature of the outer surface, this particular curvature is going to have a center. Okay. And this particular distance is going to be known as the radius of curvature, denoted by R. And this point is going to be noted as center of curvature. Center of curvature. Okay. Now, this particular point here, where the principal axis is cutting the curvature into two equal parts, this is known as pole. This particular position is known as pole. Okay. And this particular pole curvature, this is known as aperture. Okay. This is going to be termed as aperture. Suppose this is A and B. That means AB is going to be my aperture for the refracting surfaces. Okay. Now, just like what we did in with the cases of mirror, okay, in like concave or convex mirror, we have applied the new Cartesian sign convention. The same thing will be applied here. Okay, new Cartesian sign convention, okay, is also going to be applied exactly the in a same manner. Okay, so what was the new Cartesian sign convention? If you have an object from where the light is coming, okay, this is my object distance. This is going to be denoted as object distance. Now, there is going to be a particular focus point as well. Okay. And there is going to be a particular point where the image is also going to form. Okay. So, if the light is coming from this direction and I'm also measuring in the same direction, that means from pole to this direction, if I make calculation in the same direction of the light, I'm going to take it as positive. But if I take the measurement in the direction opposite to the incident light, that means in this direction, then I'm going to take the negative, okay, measurement. If anything is placed above the principal axis, that will be positive, okay, and if anything which is placed on the downside of the principal axis, I'm going to consider that as negative. Okay, so the particular things which are associated when we are going to solve these particular questions, okay, first thing is new Cartesian sign convention is going to remain exactly the same. Second, phenomena or these particular terms which are related to spherical refracting surfaces, these are much needed. Okay, so don't forget them. Now, with the help of this, okay, I'm going to show you how exactly each of the refracting surface is going to form a particular image regarding the object position. Okay. Now, I'm going to take some assumptions as well, because whenever you create large surfaces, spherical aberration happens. I told you that. So for most of my cases, what I'm going to assume that the aperture AB, which I'm going to use, is of going to be small nature. Okay. And in most of the time, I'm never going to take an object in a big amount, like above the principal axis. In most of the cases, I'm going to use a point object. Okay. So two assumptions I have, that my aperture is going to be small, or that the object which I'm going to consider is going to be a point object, and it will always lie on the principal axis, not above, not down, exactly on the principal axis. Okay. Third assumption which I'm going to make, that the incident ray, the refracted ray, and the normal to the spherical surface, they are going to make a small amount of angles with the principal axis. Whenever the light is going to travel from the object point, it is going to make a particular small angle with the in respect to the principal axis. So all these rays, incident ray, refracted ray, and the normal, it is going to consider small angles, make small angles with the principal axis. Okay. So this is our assumption based. This is our terms related to the refracting surfaces. We have seen two surfaces. One is concave, another is going to be convex. Okay. And this is the new Cartesian sign convention attached to it. Now, by using all of these things, okay, we are going to understand the refraction process through the spherical surfaces. Okay. And that is going to form our next topic. Okay. So see the next topic. See, the next topic is refraction through a spherical surface. Spherical surface. Okay. And first, in the first task here, what we are going to take a convex spherical surface here. Okay. And we are going to place our object, okay, in a rarer medium. Okay. And because of this, what kind of image is going to form, we are going to see that. Okay. So how exactly my uh, diagram is going to look like, let's see. Okay. Okay, suppose this is the surface here. Okay. And I'm going to draw the principal axis like this here. Okay. This is my principal axis, not exactly straight. One second. This is my principal axis. Suppose the object is lying at this particular point. This is O. Okay. And this particular surface is convex in nature. That means its center of curvature is going to lie inside of it. Suppose here, C. Okay. So my normal is going to pass from this particular point. Suppose this is my normal here. It is going to pass like this. Okay. Give me one second. हेलो. इसने क्लास में हूँ, 10 मिनट में खाली है. ठीक. Okay. So this is my normal passing from the center of curvature. Okay. And my object is at this point, this particular point. Now this is my medium one. This is air N1. I'm going to consider the refractive index of this particular as different. So these both have different refractive indexes. This has N1 medium. This is N2 medium. Okay. So when the light ray is going to fall, okay, at this particular point, suppose like this, it is going to fall. Okay. Now it is going to make angle of incidence. Okay. And it is going to make a particular angle of incidence in in relation to this normal. So this is going to be my angle of incidence. Now, this particular object ray, this incident ray on this particular point is also going to make an angle, okay, with the principal axis. I'm going to consider this particular angle as alpha. Okay. Now, this is my object size. So this is going to be known as u. Okay. This is my u. Okay. Now, when this light is going to enter inside this particular glass medium, what it is going to do, now the light ray is traveling from rarer to denser medium. Okay, light ray is traveling from rarer to denser medium, and because of that, what is going to happen? Okay, it is going to bend towards the normal. Okay, so there is going to be bending in the light ray, so it will bend towards the normal, and like this the bend will happen. Okay, so after bending the light, it is going to fall on the principal axis inside the denser medium, and it is going to form an image. Okay, so in this particular situation, my image nature is going to be real. Why? Because the real rays has created the image. Whenever the real rays are involved in creating an image, my image is considered as real. Okay, and whenever we are assuming the light rays has gone someplace else and we are adjusting it to a particular point, that particular image is going to be considered as virtual. So in this particular situation, when we have used a convex spherical surface, refracting surface, object has been placed inside the rarer medium, my image has come out as real. Okay, now this particular center of curvature, the normal, has made a particular angle with a principal axis. Okay, my image also has made a particular angle. We are going to call these particular angles as beta and gamma. Okay, and this particular distance for the center of curvature is going to be known as r, and this particular image distance, okay, this particular distance is going to be considered as v. Now, by applying the new Cartesian sign convention, we can understand how the process of refraction is going to take place in this situation. Okay, and when the process of refraction that will take place, okay, after doing all the calculation and everything, the result will come. Okay, and the result will come as minus n1 upon u plus n2 upon v, okay, equals to n2 minus n1 upon r. Okay, here it will show you that your object is placed inside the rarer medium, and this is a result of doing the calculation of process of refraction. And how exactly that will happen? If you apply the Snell's law, what it is going to be? It is going to be sine I upon sine R. Okay, light traveling from 1 and 2, that means n2 upon n1. Okay, now in this particular situation, you can calculate this particular uh, concept. Okay, now here I'm going to assume that the angles are very small. So in this particular situation, I'm going to assume that sine I is so small that I can exactly write it as angle of incidence, and I can write this particular situation as r. Okay, so by calculating this, you can assume the equation will become as n2r, okay, equals to n1 r. Okay, one second, n1 I, this is a mistake on my part. uh, the calculation is going to be n1 I equals to n2 r. Okay, now by applying the values of angle of incidence and angle of refraction here in this particular situation, you can calculate all these values by going into the details. You can make a particular 90-degree here, and in these triangles you can calculate the value of angle of incidence or value of angle of r. Okay, and when you place those particular values here, you will get this particular result. Okay, and this result is telling you how the refractive index of both the mediums, how the object distance, how the image distance, and how the center of curvature is related in a particular equation. These all variables are related to each other, and how exactly they are related, this is how. Okay, And when you solve this particular thing, okay, in this particular position, I have solved it for a convex spherical surface. Okay, and this is how my mirror, sorry, diagram comes out as to be. Okay, now in this particular situation, my result is this. Suppose if I take a second case in which I'm creating a particular differentiation, and that particular difference is that I'm bringing my object a little bit closer. Okay, so how exactly it will change? Let's see. Okay, suppose I'm bringing my object a little bit closer. Again, it is there is going to be C. Okay, my normal is going to pass from that particular point. Okay, if I bring my object a little bit closer like this. Okay, now I have increased the angle of incidence. That means when the light is going to fall like this, my angle of incidence has increased. Earlier, it was traveling like this and falling here, but now the angle of refraction is also going to change. It is going to become a little bit bigger. Okay, and because of that, what will happen? It will travel such a fashion like this, a little bit further from the principal axis. It is not going to now fall on the principal axis. And because of that, what is going to happen? The light is going to travel somewhere else, and when I will back trace it, my image is going to form on the same side. Okay. So this is going to make again beta angle, this is alpha angle, and this is, sorry, this is gamma, this is beta. Okay. Now the different angles made by the object image and the normal here, okay, they are going to be different. But in this particular situation, when I have increased the angle of incidence, okay, the image has changed. Okay, earlier in all the cases the image was real, but in this particular situation my image is going to be virtual. My image is going to be virtual. But when you will solve this particular equation, okay, for all the values of angle of incidence and values of angle of refraction, what really surprises is that your result will come out as same. When you will solve the whole equation, your result will come out as minus n1 upon u plus n2 upon v equals to n2 minus n1 upon r. Okay, so in both the cases, when my image was real and when my image was virtual, my equation does not change. In both the cases, equation or the result came out as equal. Okay, so there is something very peculiar happening in this particular situation. Okay, irrespective of how I am changing my positions of object, the result is not changing. Okay, so to further investigate this concept, what we are going to do now, we are going to change the position of object. Okay, in this particular situation, my object was in rarer medium. To understand this particular concept in much detail, what now we are going to do? Now we are going to change the placement of object. Okay, let's see. Okay, now instead of when I'm putting my object in rarer medium, now we are going to put our object inside denser medium. So let's see. In this particular situation, what we are going to do? This is my normal again. Okay, see, we are going to put our object inside the denser medium. Now, this light ray is going to fall from this particular point to this particular point. Okay, it will fall like this. Okay, like this. It will travel like this. Now, when the refraction will happen, it is going to travel from denser to rarer medium. That means light is going to bend away from the normal. And when that will happen, it is going to fall like this. Okay, that means my image is going to be uh, formed inside the rarer medium. That means, and also it is going to be real in nature because the real rays are involved. Okay, and when you solve this particular equation, now the angles of incidence, okay, this is your angle of incidence, this is your angle of refraction, this is your alpha angle, this is your beta angle, and this is your gamma angle. When you change solve it for all the equations of angle of incidence and angle of refraction in the same equation. Okay, now in this particular situation, when you calculate, your result comes out a bit different. Now the result which you will get, this will be as minus n2 upon u plus n1 upon v equals to n1 minus n2 upon r. Okay, and with this particular case, we have investigated to the final point that it is not the angle of incidence that is making any difference. Yes, when you increase the angle of incidence, okay, there might be change in the nature of the image. The image could be real or virtual, but the equation which relates all the variables, it is not going to change. It only changes when you change the placement of the object. Okay, if you put it inside the rarer medium, the equation is going to be different, which is minus n1 upon u plus n2 upon v equals to n2 minus n1 upon r. And if you put your object inside the denser medium, your equation is going to be totally changed. That is going to be totally different. Okay, so this particular concept has told us here the object's placement is making all the uh, necessary changes here and what really matters here. Okay, and anything else is of very less relevance. Okay, similarly you can do this particular thing for, you can also find the virtual image. Okay, if I further change the angle of incidence, also there is going to be a virtual image in the case of convex refracting surface. And further I can do the same calculations for refraction through a concave surface. Okay, we can see for one case. Let's see. Suppose I take a case of, okay, I take the case of a concave refracting surface, which is like this. Okay, this is going to be shown like this. This is my concave refracting surface, and I'm going to draw my principal axis in this particular fashion. Okay, suppose you take an object which is lying at this particular point O. Okay, and this is the point of center of curvature. So your normal is going to pass like this. Okay, when the light ray is going to come and it is going to fall like this at this point. Okay, and this is going to form your angle of incidence. This is your angle of incidence. Now the process of refraction will take place and it will bend towards the normal. So the light ray is going to go like this. That means when you will backtrace it, this is your image position. So in the very first, okay, concept here, when we took the concave refracting surface, okay, what did we observe here? We see when, if I'm taking very less angle of incidences, okay, and when I put the object in the rarer medium in the concave refracting surface, first time when we applied the same concept, my image is coming as virtual and in the same medium. Okay, and here the equation, when you will solve this particular situation, okay, for the concave refracting surfaces, equation comes out exactly the same when you put the object in the rarer medium in the convex refracting surfaces. So the equation is again going to be n1 upon u plus n2 upon v equals to n2 minus n1 upon r. Okay, now this is the most exciting point here, because in both the refracting surfaces, when you took concave refracting surface or you took convex refracting surface, it is not the amount of angle of incidence, it is the placement of the object. When you place a particular object in a rarer medium, the same kind of equations are coming, and when you put the object in the denser medium, the same kind of object or equations is going to come in. Okay, and that is our final result. The image nature might change. Okay, image nature might change, but the equation, the relation is going to depend only on one thing, and that is the object's placement. Okay, so the final result in this particular situation is that, okay, the final result in this particular situation is that if your object, okay, it is lying in the rarer medium, it is lying in the rarer medium, okay, then relation minus n1 upon u plus n2 upon v equals to n2 minus n1 upon r is valid. Okay, it is valid irrespective, okay, of type of refracting surface. Okay, you can take any type of refracting surface. Okay, if the object is placed in this medium, rarer medium, this relation is going to be valid and nothing else is here related. Okay. And the second concept tells us that if your object is placed in denser medium, then another relation which we have solved, that is minus n2 upon u plus n1 upon v equals to n1 minus n2 upon r is going to be valid irrespective of the type of refracting surfaces. Okay.